Okay, hello. So the goal of this video is to get through the outline that's right down there as quickly as possible so you can get through the worksheet that you grabbed from my mailbox. And if you can get through the worksheet that you grabbed from my mailbox, then you'll be able to do the homework this weekend. And if you can do the homework this weekend, then you'll ace the quiz next Thursday. That's the plan. So yeah, I'm just going to try to cover all these topics. Basically, yeah, let's just go. We're going to try to do it as efficiently as possible. So 4.5 is about periodic and piecewise functions. We are mainly interested in piecewise functions. We're not very interested in periodic functions. They're kind of cool, but the main thing we need to survive section 4.6, which is the big payoff, is we need piecewise functions. So all the homework problems only talk about the piecewise functions. So if you look in the section, there's a lot of stuff going on. We're just going to skip that part. We're doing the good part, piecewise functions. Okay, so the main way we're going to deal with piecewise functions in this class is with this function u of t. So u of t is this very specific function. U is not a number. U is like the name of a function. It's the function that it's like an on-off switch, but it's always either just on or just off. It's on starting at t equals 0, and it's off when t is less than 0. It doesn't really matter what happens exactly at t equals 0, but we'll say that it's on at t equals 0. So you should imagine that this is u of t is a switch that's off, 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 and then it turns on suddenly at a certain time. U of t turns on at time t equals 0. So the graph is pretty simple. It's like 0 forever, and then suddenly 1. 1. There we go. Hopefully you can see this. Okay, u of t is fine, but we don't usually use u of t specifically. We usually use a shifted version of u of t. If you move u of t over to the right by a units, then you get the same function. It's like sometimes on and sometimes off, but it turns on at a different time because you moved it over by a units. So it turns on at time a. Before time a, it's off. So the graph for this is it's 0 for a long time, and then suddenly there's some special time t equals a, and at time t equals a, it turns on, then it's 1 from there on. So u of t minus a is the on-off switch, but it's really just an on switch. It turns on at time a. If you ever need an off switch instead of an on switch, then you'll do it this way. If you do 1 minus u, so we literally do 1 minus the thing that's above here. It's not like 1 minus u as an object. It's 1 minus and then this function. All you get is 1 minus 1 is 0, and 1 minus 0 is 1, so it switches when the on and the off happens. You get, starts out 0, oops, nope. It starts off 1 for low values, and then it turns into 0 later. So we're going to need some switches that turn on and some switches that turn off in order to handle piecewise functions. So this one's 1 for a long time, and then suddenly at time a it turns off. Okay, so that's u of t. That's what's going on here. U of t showed up in your table. You saw it before. U is not a number, though. U is the name of a function, and it's this function. Okay, erasing this board is a little weird, but doing it, it's working. Okay, the main way we're going to attack piecewise functions is with Laplace transforms. If we try to use chapter 2 on piecewise functions, it's a huge disaster because we can't do undetermined coefficients with piecewise functions. It's a huge mess. So we want to find the Laplace transform of u. And I'm really interested in, oh dear, that is not what I wanted to write. I'm really not interested in u of t, again. I'm more interested in u of t minus a. I want to know what happens if there's an on switch at time t equals a. Well, the Laplace transform is like, works the same every time. You take the Laplace transform integral. It's this integral from 0 to infinity dt, and you drop the function into the Laplace transform. So you drop this u of t minus a in here. Then you deal with it the same way you've dealt with all piecewise functions. You say, oh, well, u of t minus a, it's sometimes 1 and it's sometimes 0. And the times that it's 0 we don't care about. So all that's going to happen is the function is going to be 1 sometimes, and the rest of the time it kills the whole integral. So we just look up when u of t minus a equals 1, and that's, well, starting at time a. So my handwriting on this tablet is pretty bad, but the original integral started at 0, this one starts at a. Then you just do this integral, which you've done a lot of times by now. And you end up plugging in infinity and plugging in a. When you plug in infinity, you get e to the minus infinity as long as s is greater than 0, whatever. But you get, plug in infinity, you get 0, and then plug in a, you get something slightly different, which is you're plugging in a for t, so I'm going to write it as e to the minus as. So the final answer here is that these are both plus, and this is what you get for the Laplace transform of u of t minus a. Okay, so that pretty much completes that part of the table, like the table that was originally laid out in section 4.1. Now you've seen it all. This is where it comes from. And this is what u is. Okay, so what u is good for is it's good for writing inline formulas for piecewise functions. So if you have a function, let's say you have a function that's it starts out as like 2, and then so this will be like at y equals 2, and then suddenly at time t equals 4, it turns into something different. It turns into like 5. So the function is 2 before time 4, and then it's 5 after time 4. It's kind of a weird function. You can imagine a function as like a force function in this class. So this would be like there's 2 newtons of weight hanging from the spring, and then suddenly at time 4 you like hang extra weight from the spring. So the weight goes up, force function changes suddenly. The way you do this is you say, okay, well, this function it's 2 at first. And then at a certain time, something turns on. We don't want this. This would start at 2, and then at time 4, suddenly this like extra 5 newtons would turn on. We don't want to ever get 2 plus 5. That would make it come out to 7. So this is no good. Instead, what you want to say is you want to say, okay, well, sure, the 2 newtons is working the whole time. What actually turns on at time t equals 4 is 3 more newtons. So we want 3 copies of this like on switch. I'm really sorry about the handwriting. So 2 plus 3 u of t minus 4 gives you this function that starts at 2 and then suddenly turns on and becomes 5. If you had some other function, like say you had a function that started out at 1 and then suddenly flipped and turned into 6, and then like went back and turned into 3 after that, and then we'll say these happen at time 2 and time 4. So this function is 1, 1, 1, 1, 1, and then 6, 6, 6, 6, 6, 6, 6, and then 3, 3, 3, 3, 3. This function, you could write it as a piecewise function, but we get to now write it with this u function as like, I don't know, it's easier to write. The function is just 1 at first. Then at time 2, we add 5. Then at time 4, we take away 3 more. So that looks like this. Make sure this is visible. Yeah, it looks like it's working. Okay, so you can basically build most piecewise functions out of u of t. It's pretty good. The main way that this is going to get more complicated is, what if you want your piecewise function to not just be constants all the time? Like what if you want a function, but you want the function to turn on later, like a complicated function that turns on later. So here's how this would work. If you make a function that's just t squared u of t minus 3, what this does is you get the function t squared, but it's off at first, and it only turns on at time 3. So you don't get like it's off and then suddenly a parabola starts. Instead you get it's off and then suddenly the parabola picks up where it would be at time 3, which the parabola would be at 9. So this is what you get if you have like a parabola or like any function where like you have the on switch at a certain time. The function normally would have existed all these places, but u of t minus 3 makes sure that the function is off before time 3 and turns on at time 3. So the function doesn't have any of this dotted stuff. And I erased the y-axis. That's weird. Oh well. Great, it's back. Okay. What we actually want to be able to make is a function that's delayed. To make a function be delayed, we'll need to... So like, to be able to make a function that's like 0 for a while, and then suddenly at time 3, like the parabola picks up where it normally would have been. To make that, all we have to do is use the switch to turn it on at time 3, and also shift it over by 3. Oh dear, I have no idea which way is right and left, because, okay, but it shifts to the right. So, yeah. To get this function where you've delayed a function, you shift it by 3, and turn it on at time 3. So that's what you get here. Yeah, so I should write this in a box and like, but this is the point. If you ever want a function to be delayed by a certain amount, this is how you do it. You'll practice it in a second. Okay, so f of t delayed by a, like delayed by a seconds. Uh-oh, I've got like cursive mode here or something. Wow. F of t delayed by a seconds is f of t minus a turned on at time a. Cool. One more thing you're going to need is you're going to need what happens when you do the Laplace transform of this function. Well, I'm just going to tell you instead of deriving it, because we're trying to do this really efficiently. If you do the Laplace transform of a function that's delayed, so when you see this, you shouldn't be like, oh, there's two functions multiplied together. No, you should read it as f of t delayed by a seconds, like off for a while and then suddenly on again at time t equals a. You get the original, what the Laplace normally would have been, but you also get an extra e to the minus as. So this is going to be an important thing to add to your table. You can find it in the front of the book, the like front cover of the book is where all the good ones are, and this one is like right above the convolution on the list is u of t minus a, f of t minus a corresponds to multiplying the Laplace transform by this e to the minus as. This is important in a box here. Cool. Okay, so the questions you're going to do in 4.6 that make this come up are, say you want to find, this will be an example, say you want to find the inverse Laplace transform of this thing. Let's do e to the minus 3s over s squared plus 4. This function looks a lot like the s version of sine 2t, but it's missing the 2 on top, and it has this extra e to the minus 3s. So what we do is we say, okay, well, it's off by 2, first of all, so it's going to be half sine of 2t. But this e to the minus 3s delays by 3 seconds. Then to write it as a formula, delaying by 3 seconds means you shift it and then have it turn on at time 3. So it's going to be half sine 2t minus 3, like drop t minus 3 in where t was, and then only turn it on at time 3. What's this? Okay, that about covers it for section 4.5. It's up to you if you want to, like these worksheets here, it's up to you if you want to like try to do section 4.5 now. and then watch the rest of the video later. Up to you, but I'm gonna switch to 4.6 now. Feels really weird to not ask any questions at that point, and then like try to get you to ask questions. But I'm in a different city. I can't hear you. Okay, 4.6 is about impulse functions. So the outline here is I'm first going to tell you what I know about physics as far as impulse, which is basically just how the units work. Then I'm going to show you what the Dirac delta function is and how it's useful. Finally, I'm going to skip the very end of 4.6, which was about something called Duhamel's principle. Duhamel's principle is really cool, but it's only one problem in the homework anyway, and so we're just going to cut it from the class because I missed the day, and so oh well. Okay, so first let's talk about impulse. Impulse is measured in these units. They are measured in Newton seconds. You can get, so this is Newton's times seconds. It's not Newton's minus seconds. You can get impulse by integrating a force with respect to time. Normally, you would not integrate a force with respect to time. Normally, you would integrate a force with respect to distance or displacement or something, because a force multiplied by a distance is work. So normally when people talk about integrating force, they're talking about work. But here, well, if you integrate force, you get impulse. So like 4 newtons, and you like push with 4 newtons of force, you push for like 10 seconds, that's an impulse that you did. You did, like, even if I push like on my head and it doesn't move, right? I do like 4 newtons of force and my head doesn't move. I'm doing no work, but I'm doing an impulse. 4 newtons for 10 seconds is 40 newton seconds of impulse. Okay, the weird thing about Newton seconds is that the units are exactly equal to kilograms times meters per second. Like the seconds cancel one of the seconds that are inside of newtons. And kilograms meters per second is mass times velocity, which is momentum. Now, momentum and impulse are not the same thing. If you want to go into the details of like how exactly they're different, I'm going to tell you the way I think about it, but you should not trust me. I should be like last place on your list of people that you trust for like exactly how you're supposed to think about physics units. You should talk to like a physics expert. But the thing I understand about impulse and momentum is that you should think about impulse as a change in momentum. So if you start with like, let's write that, impulse is a change in momentum. Like if you're trying to use the fact that the units are equal here. So if you have an object that starts with like it's like a 10 kilogram object and it's moving 2 meters per second. So you've got 20 kilogram meters per second of momentum, and then you hit it with a hammer and it makes it go faster. Like it's going past you at 2 meters per second, and then you like whack it with a hammer and it speeds up. You added momentum to it. This amount of momentum that you added to it, that's an impulse. An impulse of 10 Newton seconds is like the change. So that's how we're going to think about impulse. Impulses are interesting because you can actually give something an impulse at an instant. If I like push myself like this, well, okay, I like applied a force over like a long period of time. But if I just like hit an object like all in one instant, like, okay, I probably shouldn't have, well, I don't know what's going, whatever. Okay, if you hit an object in an instant, you're giving it an impulse, but it's happening over like a really short period of time. So the integral is not going to be a good way to do that. So let's see. See like why I'm talking about this. The reason I'm talking about this is I need to be able to write a function that puts like a hammer strike into my force function. Yeah. So if my force function looks like this, where like there's no force for a while, but there's like some force for a while between times 2 and 4, and then there's no force again. Let's say you had like 10 newtons. Then the area under this graph represents the impulse. We pushed with 10 newtons for a duration of 2 seconds, so this is an impulse of 20. if this is the force of 10. If you hit something with a hammer, then the force function looks a lot different. Like say at time 3 seconds, you hit something with a hammer, and you give it 20 units of impulse. Well, there's no force, no force, no force. Then suddenly something weird happens, and then there's no force, no force. It's going to be really hard to draw a function that only is non-zero at one single time, but still has an area under it of 20. You have to like make some ridiculous function like this. This is not a function because it doesn't really have function values. All it has is like it's 0 most of the time, and then at time 3, it's so high into infinity that the area under it is 20. That's not like a function object. It's a perfectly reasonable object. It's called the Dirac delta function, named after this person, Dirac. I don't know why it's called the delta function. I think it's just because we use the Greek letter delta to write it. So a delta function will be something like this, that lets us have an impulse all at a certain moment. Okay. If I write just delta of t, get that down there. So delta of t. Delta of t is this function. It's the function that where there's no force and there's no force, but there's just enough impulse at time 0 to get 1 unit of impulse. So this is a unit impulse at time 0. If you want a unit impulse at a different time, you just move it over. So you get like, if you want a unit impulse at time t equals a, no problem. Shift it by a. Now there's no force, no force, no force. And then at time a, it's like infinite much force because you hit it with a hammer. And then there's no force again. This is the unit impulse. Unit meaning 1, like impulse of 1 at time a. Finally, if you want like a different amount of impulse, you want like 20 Newton seconds of impulse, well, you just multiply it by 20. This is 20 Newton seconds at time a. So this is a new kind of object. This new kind of object, it's not a function, so it really would not have worked well in chapter 2 when to deal with these functions we did undetermined coefficients by like taking derivatives and stuff. This is not a function. Its derivative would be a huge mess. It's not a thing. So yeah, so we have to use Laplace transforms to deal with piecewise functions like this, or piecewise functions like in the last section, and weird like functions with air quotes like the delta function in this section. These are the main benefits to using Laplace transforms. So they handle weird functions better. Okay, so big surprise, we need to find the Laplace transform of the delta function. So we need to know what Laplace of an impulse at time a is. Well, no problem. We'll just drop the delta function into our Laplace integral. Which is an integral from 0 to infinity. Now, the thing about our integral from 0 to infinity is this function, I have to keep saying function with like air quotes in my mind, but this function delta of t minus a, it's 0 almost all the time. It's like always 0, except at time t equals a. So what happens when you integrate and multiply by a delta function at time t equals a is you just get to plug t equals a into the function. Really weird. Certainly this integral, it can't involve anything other than t equals a, because the delta function only happens at t equals a. So what can we do if all we have is just t equals a? Well, it turns out that what we get to do is just plug in t equals a. So we get just e to the minus as. So this is the second to last important thing you're going to put on your table. is the Laplace of a unit impulse at time a is e to the minus as. You should notice that this e to the minus as is the same thing that appeared in the previous section. E to the minus as is like an indicator that something has been delayed. Yep, in fact, the special case here would be, what if the unit impulse is at time 0? If the unit impulse is at time 0, then you get e to the minus 0s. So the Laplace of the delta function at time 0 is just 1. So we did it. We know how to find the Laplace of 1, but we also know what function has a Laplace of 1. It's the like precise hammer strike of with 1 unit impulse happening at time 0. That's how you get 1 in your Laplace world. Okay, so let's build some problems. Actually, let's build one problem, and then I'm gonna send you off to do the rest yourself. So to do this problem, writing words on this tablet is really not going very well, so I'm gonna say the words, I guess, and then write the differential equation. So I'm gonna say you've got a 1 kilogram mass, and you've got a spring that, like, sometimes, remember, you'll get the information about the spring constant different ways. Like, it'll tell you how far it stretches under a certain force, but I'll say you've got a 1 kilogram object and a spring that has a strength of 9 newtons per meter. And it's just sitting there quietly. You don't put any force on it at all until suddenly, at like time 2, you smack it with a hammer and you give it, let's say 12 Newton seconds of impulse. Uh-oh, I can't remember what time I said. I probably didn't say time 3, probably time 2. We're gonna make it time 2. So we're gonna give it an impulse at time t equals 2. Other than that, we'll just like let it sit there. So we'll say this object, it was at rest. It's completely at rest at the start. So what's going to happen? Well, if you have an object, it's attached to a spring. I don't have the spring with me. You have an object attached to a spring. It's just sitting there, and you just sit there and wait for a second, and then you suddenly hit it. What's going to happen is it's going to sit there quietly and then suddenly start oscillating when it gets hit. So we're expecting the answer to be, oh, x is like 0 for a long time, and then after you hit it, it starts oscillating. So let's see how that works. We'll just Laplace everything. To Laplace x double prime, we're going to get minus some initial conditions, minus s times the other initial condition, plus s squared capital X. Then Laplace of 9x is 9 capital X. And then Laplace of 12 times a function, well, the 12 is going to survive. And then delta of t minus 2, its Laplace transform is just e to the minus 2s. To solve this for capital X, that stuff is all 0. We're going to divide both sides by s squared plus 9. And then what you get on the right side is exactly the Laplace transform of a function that's been delayed in time. So it's supposed to have a 3 on top, so we've got like 4 times as much. Like if you go back to t world, we've got 4 times as much as a sine 3t would have. But e to the minus 2s means it's delayed by 2. So to get it typed in to a computer to graph it, or to give a final answer without English words in it, you need to take sine of 3t, shift it by 2, and make sure it only turns on at time 2. And this will give us the function that we're expecting, which is for it to be 0 for a while, and then suddenly at time 2, it gets hit with an impulse, and so it starts oscillating. That's that. The homework problems are pretty reasonable. The worksheet problems get pretty hard, so hopefully you have somebody to talk to here to deal with number 4. The main thing is you're going to need to think about what the units are for impulse and momentum, because this problem number 4 says it doesn't tell you exactly how big the impulse is. Instead, it tells you how fast it sends the object. So think about what its momentum is, and that'll tell you how big the impulse was. Yeah. Okay, that's all I got. It's 30 minutes, hopefully. So hopefully you have enough time to get through all these problems, and then you can send me questions. Unfortunately, I'm not going to get to email until probably really late Sunday or maybe even Monday, but try to work together and see how this goes. Hopefully this goes pretty well. I'm going to have the quiz for you on Thursday, so bring me questions on Tuesday. Okay, cool, thanks. Have a good day.